So let's apply the transformation. So we have that the transpose of the vector x prime times the diagonal matrix D times the vector x prime is 8 times x prime squared minus 2 times y prime squared. So let's calculate the transpose of the vector j times the matrix P times the vector x prime. The transpose of the vector j is the row vector 14 minus 2, or negative 2, times the matrix P times the column vector x prime, y prime. So we have 14 times 2, square root of 2 over 2, which is 7 times the square root of 2, plus 2 times the square root of 2 over 2, which is the square root of 2. So that's 7 plus 1, or 8 times the square root of 2 as the first component. And then 14 times the square root of 2 over 2, again 7 times the square root of 2, minus 2 times the square root of 2 over 2, or minus the square root of 2, and so that is 6 times the square root of 2 times the vector x prime, y prime. And so that is the scalar 8 times the square root of 2 times x prime plus 6 times the square root of 2 times y prime. And so the equation in the transformed coordinate system for our hyperbola is 8x prime squared minus 2y prime squared plus 8 times the square root of 2 times x prime plus 6 times the square root of 2 times y prime plus the constant 3 is equal to 0. So let's put this equation in its standard form. And so we have 8 times the quantity, x prime squared, plus the square root of 2 times x prime, minus 2 times the quantity, y prime squared, minus 3 times the square root of 2 times y prime, plus 3 is equal to 0. So let's complete the square for each of the coordinates. So we have 8 times the quantity, x prime plus the square root of 2 over 2 squared, minus 2 times the quantity, y prime minus 3 times the square root of 2 over 2 quantity squared, plus 3. And to keep the equation in balance, we need to subtract 8 times the square of the square root of 2 over 2, which is 1/2. So 8 times 1/2 is 4. And we need to add 2 times the square of 3 times the square root of 2 over 2, which is 9/2. 2 times 9/2 is 9. And so we have 8 times the quantity x prime plus the square root of 2 over 2 squared minus 2 times the quantity y prime minus 3 times the square root of 2 over 2 squared is equal to negative 8. And so we have the quantity y prime minus 3 times the square root of 2 over 2 squared all over 4 minus the quantity x prime plus the square root of 2 over 2 squared all over 1 is equal to 1. And so now we can recognize that we have a hyperbola with a vertical transverse axis, and the equation of the vertical transverse axis can be determined by setting this quantity equal to 0. And so we have the equation for the vertical transverse axis is x prime is equal to negative square root of 2 over 2. So to determine the transverse axis for the original, in the original coordinate system for our hyperbola, we need to apply the passive transformation. So we applied the vector x is equal to p times the vector x prime, and so the vector x prime is equal to the inverse of p times the vector x. So we have x prime, y prime is equal to the vector, or rather the matrix, the inverse of P, which is the square root of 2 over 2 minus the square root of 2 over 2. That is, the first column becomes the first row, and square root of 2 over 2, square root of 2 over 2 as the second row, times the vector xy. I can rewrite this as the scalar 2 times the square root of 2 over 2 times the matrix 1, negative 1, 1, 1 times the vector x, y. So that's the square root of 2 over 2 times the vector x minus y as the first component, and x plus y as the second component. So for our equation, our x prime, we want to replace with the square root of 2 over 2 times the component x minus y, and set that equal to negative square root of 2 over 2. So this simplifies to x minus y is equal to negative 1, or y is equal to x plus 1. So the transverse axis in the transformed coordinate system is x prime equals negative square root of 2 over 2, and in our which corresponds to the transverse axis y equals x plus 1 in the original coordinate system for our hyperbola. Now again, the original transformation that we applied is that the vector x is equal to p times the vector x prime. So that's the scalar square root of 2 over 2 times the matrix 1, negative 1, 1, 1 times the column vector x prime, y prime. So that's the square root of 2 over 2 times the vector x prime plus y prime as the first component, and negative x prime plus y prime as the second component. Now I'll write that as y prime minus x prime. And so we can use this transformation to transform points in the vector x prime coordinate system to the original coordinate system. So let's again look at our transformed equation. We see that the center is given by negative square root of 2 over 2, square root of 3 times the square root of 2 over 2. And so in our original coordinate system, so the center in the transformed coordinate system is negative square root of 2 over 2, 3 times the square root of 2 over 2. So if we add the x prime and the y prime, that will give us 2 times the square root of 2 over 2. And if we take our y prime coordinate minus our x prime coordinate, we have 3 times the square root of 2 over 2 minus the square root of 2 over 2, or minus negative rather. So that gives us 4 times the square root of 2 over 2. And if we bring out the scalar, the square root of 2 over 2, and multiply it with the existing scalar, the square root of 2 over 2, we have 1/2 times the vector, the vector 2, 4, which gives us the vector 1, 2. And so the point negative square root of 2 over 2, 3 square root of 2 over 2 is transformed to the point 1, 2 in the original coordinate system. So now let's look at the vertices. The vertices for a hyperbola with a vertical transverse axis is given as the points h, k plus or minus a are a squared is 4, so a is equal to 2. So one of our vertices in the transformed coordinate system is the negative square root of 2 over 2, 3 times the square root of 2 over 2 minus a, or minus 2. So this is the point negative square root of 2 over 2, 3 times the square root of 2 minus 4, all divided by 2. And so by symmetry, the second vertex is negative square root of 2 over 2, 3 times the square root of 2 plus 4, all divided by 2. And so, again, we'll use our transformation to determine what these points are in the original coordinate system. And so the point xy is the square root of 2 over 2 times the vector x prime plus y prime. So that's negative square root of 2 over 2 plus 3 times the square root of 2 minus 4 all over 2. That'll give us 2 times the square root of 2 minus 4 all over 2 as the first component. And then for the second component, we have y prime minus x prime. So that's going to give us 2, rather 3 minus a negative 1 gives us 4 times the square root of 2 minus 4 all over 2. So if we bring out the scalar 1/2 that's currently in the vector, we'll have a new scalar square root of 2 over 4 times the vector 2 times the square root of 2 minus 4, 4 times the square root of 2 minus 4. So that's 1/4 of the vector. 2 times the square root of 2 times the square root of 2 gives us 4, minus 4 times the square root of 2. And 4 times the square root of 2 times the square root of 2 gives us 8, minus 4 times the square root of 2. So that gives us the vector 1 minus the square root of 2 and 2 minus the square root of 2. And so the vertex in the transform coordinate system, negative square root of 2 over 2, 3 times the square root of 2 minus 4, all over 2, is transformed to the point 1 minus the square root of 2, 2 minus the square root of 2. And so by symmetry, the vertex given by in the transform coordinate system as negative square root of 2 over 2, 3 times the square root of 2 plus 4 all over 2 is the point 1 plus the square root of 2, 2 plus the square root of 2 in the original coordinate system. So let's check our work. Our hyperbola in the original coordinate system is 3x squared minus 10xy plus 3y squared plus 14x minus 2y plus 3 is equal to 0. We calculated that the center is the point 1, 2. We also calculated that the transverse axis is occurs on the line y is equal to x plus 1. We calculated the vertices. One of the vertices is the point 1 minus the square root of 2, 2 minus the square root of 2, and one of the vertices occurs at the point 1 plus the square root of 2, 2 plus the square root of 2. So we see that our calculations were correct. So we see that relative to the original equation, the transformation that we apply with the matrix P results in a rotation by pi over 4 radians plus a translation. So we can see the translation most clearly by focusing on the center. Once we've applied a rotation by pi over 4 radians counterclockwise, we must then come left and up to reach the new center. And so the transformation applied by the matrix P simultaneously rotates the hyperbola by pi over 4 radians and translates it left and up. So now that we have very thoroughly explored the conics, we will now transition to the two-dimensional analogs of those conics, which we call quadric surfaces. So a quadric surface is a two-dimensional object that is embedded in three-dimensional space. In three-dimensional space, in our typical coordinate system, we have three mutually perpendicular axes, and so we will always have three mutually perpendicular planes: the xy plane, the xz plane, and the yz plane. And so if we take a slice through a surface with a plane that is parallel to any one of those three planes, then we have what's called a trace, and that trace is going to be a conic. Well, for our quadric surfaces, that trace is going to be a conic, a curve in a plane. So for an ellipse, each of the possible traces results in an ellipse. So for example, if we isolate to a plane parallel to the xy plane, then in the xy plane we have an ellipse. If we look at a plane parallel to the xz plane, then we have an ellipse. And if we look at a plane parallel to the yz plane, then we have an ellipse. Now with a paraboloid, there are two types. In both cases, in two of the possible traces, we will have a parabola. But in the case of an elliptic paraboloid, one of the traces is an ellipse. And in the case of a hyperbolic paraboloid, one of the traces is a hyperbola. And there are two ways to have a hyperboloid. It can exist as one continuous surface. We call that a hyperboloid of one sheet. Or it can exist as two separate surfaces, two branches, say, of the surface. And we call that a hyperboloid of two sheets. Now, in both cases, there will be two traces that is going to be a hyperbola, but one of those traces will be an ellipse. And as we will see, in the case of a hyperboloid in two sheets, whichever variable that has a negative sign in front of it, that variable will not be able to assume values for anything between, in this case, negative c and c.